Alternating series test. Let's jump into it, the alternating series test, or AST. The series, the sum of n equals 1 to infinity of -1 raised to the n plus 1 times b to the n, which in expanded form looks like b sub 1 minus b sub 2 plus b sub 3 minus b sub 4, and so on, converges if all three conditions are satisfied. First, if b sub n is greater than 0. So let's come back up here. B sub n is being multiplied by this alternating factor. So this first condition really just guarantees that we have an alternating series. As long as b sub n is positive, then multiplied by the alternating factor will create an alternating series. The second condition, b sub n is greater than or equal to b sub n plus 1 for all n greater than or equal to some capital N. This is really just saying that b sub n is eventually decreasing. So remember, for infinite series, we really care about what's happening at the tail end. So as long as those individual values are eventually decreasing, our second condition is satisfied. And finally, the limit as n approaches infinity of b sub n equals 0. So those individual values are approaching 0. Let's talk for a minute about intuitively why the alternating series test works. So let's kind of imagine we're starting here and we are adding some value, we'll call it b sub 1. Well, then we're going to subtract b sub 2, which is going to be a smaller value. So I'm going to go in the backwards direction here. Let's say some amount b sub 2. And then I'm going to go forward. So let's think about it as taking a step forward, but it's going to be a smaller step forward. And then we're going to take a step back, but it's going to be a smaller step back. So you can think about it as taking these steps that keep switching direction, but shrinking in size. So you never wander off infinitely because each step gets smaller, and this back and forth motion traps you near a single point. A couple of last things. Let's make sure we look out for other alternating factors like -1 to the n, cosine pi n, and sine of pi n over 2. And there are many others, so just be aware there are other alternating factors. And then finally, a note that's very important is that a series cannot diverge by the alternating series test. We can only get converges if all of these conditions are met. In our first example, we're being asked, does the sum of n equals 1 to infinity of -1 to the n times 1 over the 7th root of n converge or diverge? Well, this has an alternating factor, -1 to the n, so it's a good candidate for the alternating series test. Let's go ahead and identify what b sub n is. So b sub n is the rest of the general term without the alternating factor. So let's take a close look at it. The first condition is that b sub n needs to be positive. So 1 over the 7th root of n is greater than 0 for n values greater than or equal to 1. And that's when our series begins at n equals 1. The second condition is that b sub n must be greater than or equal to b sub n plus 1. Or we said this means b sub n is eventually decreasing. Well, our b sub n is constant on top, so 1 over the 7th root of n is a nice candidate to check using a direct type of comparison. We have 1 over the 7th root of n compared to 1 over the 7th root of n plus 1. And because the denominator here is bigger, the overall fraction is going to be smaller. So we do have the correct direction on the inequality for values, again, n greater than or equal to 1. But basically, we just needed this to occur eventually, and it happens for all n greater than or equal to 1. Now, the third condition is that the limit as n approaches infinity of b sub n, or 1 over the 7th root of n, must equal 0. And here, again, because the top is constant and the bottom is a function of n that's just getting bigger, the overall limit does go to 0. So we can conclude by the alternating series test, which I'm going to abbreviate AST, the series converges. Here we're being asked, does the sum of n equals 1 to infinity of 2n times cosine of pi n all over 4n squared minus 3 converge or diverge? This is alternating. The alternating factor is cosine pi n, and our b sub n is going to be 2n over 4n squared minus 3. So if I focus on that, 2n over 4n squared minus 3 is greater than 0 for n values greater than 1. If I think about plugging in 1, 2 times 1 is positive, 4 times 1 minus 3 is positive. So this is true for n greater than or equal to 1. The second condition is that b sub n must be greater than or equal to b sub n plus 1, or b sub n is eventually decreasing. Now, unfortunately, on this example, we're not going to be able to do the same type of direct comparison as the last example, and that's because this numerator here is a function of n. If I think about 2n over 4n squared minus 3 compared to the n plus first term, 2 times the quantity n plus 1 over 4 times n plus 1 squared minus 3, we can't draw a direct conclusion right away that this is greater than or equal to the other side because the numerators are different and the denominators are different. So it's not quite as clear cut. And so we're not going to be able to go that route. What we're going to have to do is remember from Calculus 1 that a function is decreasing if its derivative is negative. But our function here is a discrete function, and our work in Calculus 1 was on continuous functions. So I'm going to have to take a moment and let f of x be 2x over 4x squared minus 3. We're going to consider the continuous function now so that we can go ahead and take its derivative and draw our conclusion. So our derivative is going to be found using the quotient rule here. F prime of x is 4x squared minus 3, the bottom function, times the derivative of the top 2, minus the top function 2x, times the derivative of the bottom is 8x, all over the bottom squared. Now in the numerator, I'm going to distribute the 2, and that's going to leave me with 8x squared minus 6 minus 16x squared, all over 4x squared minus 3 squared. I have like terms in the numerator, leaving me with negative 8x squared minus 6 over 4x squared minus 3 squared. All right, in the numerator, I can factor out a negative 2. So I have negative 2 times the quantity, 4x squared plus 3, all over 4x squared minus 3, all squared. Let's take a moment to convince ourselves that this entire quantity is going to be negative. 4x squared plus 3, doesn't matter what x I plug in here, this quantity is positive. This quantity down here, 4x squared minus 3, is all being squared. So that quantity is going to be positive. But all of that is multiplied by negative 2. So no matter what we substitute in for x, this whole quantity will be negative. So that tells us that f of x is decreasing. And by extension, we know that the discrete function that is basically behind this continuous function is also decreasing. So f of x is decreasing, which is going to imply that b sub n is eventually decreasing. So the second condition is satisfied. Now, the third condition is that the limit as n approaches infinity of 2n over 4n squared minus 3 must be equal to 0. Well, it is. If we think about our dominance laws, we have n to the first on the top and squared on the bottom. If the bottom of a fraction is growing bigger faster than the top, then this whole thing is going to 0. Or we can use L'Hopital's rule to verify this as well, or do a little bit of algebra. Bottom line is this limit is equal to 0, so we can say by the alternating series test, the series converges. Here we want to know, does the sum of n equals 1 to infinity of negative 1 to the n minus 1 times 5n all over 7n minus 3 converge or diverge. We have our alternating factor, negative 1 to the n minus 1, and so the remaining part, b sub n, is 5n over 7n minus 3. Now the first condition, b sub n, is equal to 5n over 7n minus 3. Well, that is greater than 0 for n values greater than or equal to 1. So the numerator will be positive. 7 times 1 minus 3, that's going to be positive. The second condition, we are going to have to use a derivative, just like the last example, because the numerator is a function of n, and it won't be a clear-cut direct comparison. So in order to show that b sub n is decreasing, we're going to go ahead and let f of x equal 5x over 7x minus 3 be the corresponding continuous function, and we're going to find the derivative. So f prime of x is equal to 7x minus 3 times 5, so bottom times the derivative of the top, minus the top 5x, times the derivative of the bottom 7, all over the bottom 7x minus 3, all squared. So we have, distributing the 5, we have 35x minus 15 minus 35x over the quantity 7x minus 3, squared. The 35x's cancel, so just negative 15 over 7x minus 3 all squared. All right, well, this is always negative. The denominator is always positive. The numerator is a constant, which is always negative. So this is always less than 0. So f of x is decreasing. And again, by extension, b sub n is decreasing as well. Because if the continuous function is decreasing, then the discrete function that's like right behind it with those integer values is also decreasing. Now, the third condition is that the limit as n approaches infinity of 5n over 7n minus 3 must be equal to 0. But it's not. So here I have n to the first on the top and n to the first on the bottom. The degrees are the same. So towards infinity, we're going to be able to take the coefficients here as our answer. So 5 over 7 is not 0. So the alternating series test doesn't help. I can't say that this diverges by the alternating series test. I can only converge by the alternating series test. So it turns out what we should have done, and what we should always do, is apply the test for divergence first. So the test for divergence would have had us look at the limit of the entire general term. So if we looked at the limit as n approaches infinity of negative 1 to the n minus 1 times 5n over 7n minus 3, well, we know that without the alternating factor, we get 5/7. So what the alternating factor does is it makes these terms alternate and get closer to positive 5/7 and then negative 5/7, positive 5/7 and negative 5/7, which means that towards infinity, this limit will not exist. And if the limit is anything other than 0, if this does not equal 0, then by the test for divergence, the series diverges. So again, we cannot say that a series diverges by the alternating series test. We have to use another test, in this case, the test for divergence, which we should have done first so that we didn't waste our time checking conditions 1 and 2. For this example, does the sum of n equals 1 to infinity of n over negative 2 raised to the n plus 1 converge or diverge? Let's break apart the denominator here so we can clearly see the negative factor. So negative 1 to the n plus 1 times 2 to the n plus 1. All right, so now our b sub n is n over 2 to the n plus 1. And that is going to be greater than 0 for n values greater than or equal to 1, where our n value starts. For our second condition, we are going to need to show that b sub n is decreasing. But again, because the numerator is a function of n and the denominator is a function of n, we're going to need to do this using derivatives. So let's let f of x be equal to x over 2 to the x plus 1, and then we'll find the derivative using the quotient rule. So f prime of x is equal to the bottom function, 2 to the x plus 1, times the derivative of x on the top is 1, and then minus the top function x times the derivative of the bottom. The derivative of 2 to the x plus 1 is natural log of 2 times 2 to the x plus 1. And then technically the chain rule, the derivative of the inside is 1, so that's not really going to change anything here. And then all over the bottom squared, 2 to the x plus 1 all squared. Now here, I'm going to want to factor out the 2 to the x plus 1 that's in both terms. There's two terms here in the numerator, and they both have a 2 to the x plus 1 in common. So 2 to the x plus 1, and what's left over is the quantity 1 minus x natural log 2 over 2 to the x plus 1 all squared. Since we factored out 2 to the x plus 1 and now it's a factor, I can cancel it with one of the copies in the denominator. So what I have left is 1 minus x natural log 2 over 2 to the x plus 1. The denominator is an exponential, so that's always positive. So we're trying to show that this is eventually negative. So what I really want to show here is I want to show that 1 minus x times natural log 2 is eventually less than 0, because I know the denominator is always positive, so I need the numerator to be negative. So let's solve this inequality. Notice it's a linear inequality. It just has an x in it. So we can solve for that x by subtracting 1. So I have negative x ln 2 is less than negative 1. Then I'll divide both sides by a negative or multiply by a negative, which will flip the inequality. X ln 2 is greater than 1. And then I'll divide by natural log 2. So x is greater than 1 over natural log 2. So for x values bigger than 1 over natural log 2, f of x is decreasing. So what we know is that f of x is decreasing when x values are greater than 1 over ln 2. Well, that means b sub n is eventually decreasing. So the second condition is satisfied. And the third condition is that the limit as n approaches infinity of n over 2 to the n plus 1 must equal 0, and it does. So the numerator is just a polynomial, n to the first. The denominator is a exponential, which is growing bigger much faster. So by the laws of dominance, this whole thing goes to 0. So by the alternating series test, the series converges. Now, the last example, in terms of the alternating series test, is really just like all the rest. We're only going to do it to practice more derivatives. We're being asked, does the sum of n equals 1 to infinity of negative 1 to the n plus 1 times n squared over n cubed plus 1 converge or diverge? So we have our alternating factor in front and our b sub n behind it. So let's look at b sub n as n squared over n cubed plus 1. And that is pretty obviously always greater than 0 for n values greater than or equal to 1. And now we have to determine whether b sub n is decreasing. And because this numerator is a function of n, I cannot do a direct comparison. We're going to go ahead and let f of x equal x squared over x cubed plus 1. We'll look at the derivative of this continuous function to see where that's negative. So we're going to do the quotient rule. We'll look at f prime of x as the bottom function, low d high. The derivative of the top is 2x minus the top function high, 2x d low. The derivative of the bottom is 3x squared all over the bottom squared, x cubed plus 1 squared. So however you learn the quotient rule, you heard me saying the little shortcut, low d high minus high d low over low squared. Or if you learned, bottom derivative of the top minus top derivative of the bottom over the bottom squared. However you learned it, this was the quotient rule. and then we will distribute in the 2x. So we have 2x to the fourth plus 2x minus 3x to the fourth all over x cubed plus 1 squared. Combining like terms, I have 2x minus x to the fourth over x cubed plus 1 squared. And now I need to think about, when is this negative? Well, the denominator is always positive, so let's focus on the numerator here. I'm going to rewrite the numerator as x times 2 minus x cubed all over x cubed plus 1 squared. So what I want to know is, so I'm going to bring this work up here, when is x times 2 minus x cubed less than 0? That's what we're solving. This is not a linear inequality. How do we determine where this is less than 0? Well, we can either attempt to graph it, but what we usually do is a sign analysis. So we need to find the zeros and put the zeros on a number line to create a sign analysis. So one of the zeros is just x equals 0. So in other words, I'm setting each of these factors equal to 0. And then 2 minus x cubed, when is that equal to 0? So we have 2 is equal to x cubed, adding that to the other side, and then solving for x, it's the cube root of 2 is equal to x. So again, what we would normally do is put this on a number line, and we would plot 0 and the cube root of 2, and we would pick test points in each interval. But we can actually do a bit of a shorter analysis, because we just want to show that eventually, so towards the tail end, that the derivative is negative so that the original function is decreasing. So I'm really only concerned about this final interval over here. So I'm just going to pick a test point over here, and I'm going to ignore these other intervals that we would have cared about in Calculus 1. If I pick a test point over here, I don't want to think too much about it. I mean, what's a number that's definitely bigger than the cube root of 2? I don't know, how about 10? So we're going to substitute 10 into this function right here to determine if we get out a negative value, because again, we know the denominator is always positive, so we need this numerator part to be negative. So I have 10 here, and then 2 minus x cubed. Well, 2 minus 10 cubed, that's definitely negative. 2 minus 1,000. So I have a negative times a positive, so yep, overall, this part is negative. And we were checking the sign of f prime of x there. Right? So the sign of f prime of x is negative. So what that means is that f of x is decreasing for x values greater than the cube root of 2. So that implies that b sub n is eventually decreasing. So the second condition is satisfied. The third condition, the limit as n approaches infinity of b sub n squared over n cubed plus 1, that's 0. So we have n squared on top, n cubed on the bottom. Bottom's getting bigger faster. The whole limit goes to 0. So by the alternating series test, the series converges.